Hi everybody, welcome back to what's going to be part 10 and the final part of our Amplifier series. Now remember, in part 9 we added an adjustable bias circuit which allowed us to get rid of that crossover distortion, and you'll have to go back and watch the parts because I'm not going to repeat myself on this. I want to get through this because there's a lot of other material coming up you'll see before we finish this. And also we attached the bias diodes to the heat sink so they have a little bit of thermal tracking. Not ideal because you'd be better off if you could attach them to the drivers, but those tiny little driver transistors don't really get warm and they're really tiny and not really conducive to attaching thermal tracking diodes. Another thing we could have done was to add a what's called a VBE multiplier instead of the diodes. And you've seen those in other videos of mine. I'm not going to get into all of that in this video. But when we were done, we had a fairly, what I would call a working example of a quasi-complementary push-pull amplifier. It is still far from perfect, and we're going to see why. There's a lot of inherent flaws in this design right now that we're going to have to correct if we really wanted this to be something that you would want to have listen to. But it is listenable. It is a usable amplifier. You could use it as is, and the average person, as long as you're not cranking the volume up too loud, it would sound pretty good. All right, so let's look at a couple numbers here. If we go back to our test of feeding just a tiny little signal. So I'm going to feed 10 millivolts RMS into this. And if you remember, this thing had insane amounts of gain, way too much for a proper power amplifier. You really want your gain to be somewhere around 20 to 30 at the most. This thing is in the order of about a gain of 80. For a 20 watt amplifier, a gain of 80 is just too much. It's great if you're using a very low output, old-fashioned cell phone, or MP3 player, those ones that didn't have very high output. But anything other than that, it's way too much. I have a dummy load connected to it right now, and I have the distortion meter. And where we left off, at very low power, if I turn on the signal, you can see we have a pretty nice looking waveform. I mean, there's no crossover distortion, at least it's visible. And of course, this cord is just so loose up here. So you can see we have a pretty nice looking waveform. And they fall right on top of one another. Pretty nice. Not too bad. It's a teeniest little bit different, but they're very close. And some of that is because the connector that I'm using up here is loose and kind of janky, so it affects the signal a little bit. You can see how it's wobbling around. If I wiggle this cable, it's pretty bad. So you'll have to forgive that. And however, though, when we get it to sit stable, if we go over to our distortion meter, we have a rather respectable amount of THD at low power. Now, as I increase the power a little bit, so we go, let's say, to 100 millivolts, and change the range of the meter, it's still respectable. It's still staying within about 1.13% THD, and if you look at the amount of the output power, it is about 7.4 volts RMS. So at about 6.8 or just around 7 watts per channel. We're still sticking around, 0.1%. And if I go to just under clipping, right there, it still stays within 2.2% THD. And that's right there is about 21 watts per channel. Not bad. Now for the not so good part, you can see These transistors are already running a little bit warm, close to about 110 degrees Fahrenheit. And if I would have left that, and that was just for the 10 seconds or so that we were showing it on the camera, if I were to leave this on for very long, these would get very hot. They're already pretty hot to the touch. I mean, 110 degrees Fahrenheit, it's pretty hot to the touch. So these will just sit there and cook. These heat sinks are way underrated. And if you look, I even put some spacers underneath them and put some better transistors. These are 2N3773s, which are a lot more durable than the original horizontal output black and white TV transistors that they were using here originally. And even with having the extra airflow and everything, these still run way too hot. So this amp is not very practical unless you're going to run it at about 5 watts per channel to 8 watts per channel tops. No more than that. Even though this is capable of 21 watts per channel or so, it's just too much. Too much for these heat sinks. If we look at DC offset, again, it's probably drifting around a little bit, but yeah, you could see 12 millivolts. It's just millivolts. I don't know if you could see that. And that can be adjusted down to 0. I didn't really mess with it much. So it's a functional amplifier, but here's the problem. That was all at 1 kilohertz. Let me go back down to about 50 millivolts. So you're going to just only be putting out maybe 2 or 3 watts, maybe under 4 watts per channel. And if I take the frequency from 1 kilohertz up to 10, okay, so let's go up to the scope. And I turn this on, you can see now we have 10 kilohertz. And if I go over to here, even at 4 watts, our nice respectable 0.13 or whatever is more than double. So at higher, and as the higher you go in frequency, here's 20 kilohertz. Now it can't read it because the meter can't pick up on that high of a frequency, but at 10, I mean, you can see you have distortion issues. In addition, if we go into sweep and we look at this, the amp is not super duper linear, but it's not bad. I guess it's respectable. Okay, so it is linear. Never mind. It is a little bit linear. So all in all, it's a listenable amplifier. I mean, it's okay, but not perfect by any stretch. So what if we wanted to take this thing to the next level and actually try to make something that could be on par with what you would purchase, a retail 15 or 20 watt per channel amplifier, let's say like from the 1970s that used this type of topology, something like a Pioneer SX450 or a Marantz 2215 or any of those really nice Magnavox amplifiers that were in some of the console receivers, stereos, anything like that. Can we do something that would make this be a little bit better? Well, you know me, I get carried away. And so I thought I'll try to do with the best I can to try to make something that will be functional, and we'll deal with all of the problems that comes with this, and then we'll go over what those things are. So this is what I came up with. The Bootyfab Labs DIY OCL amplifier by Amplifier. Okay, yeah, I got completely carried away on this. This is not something that I'm doing so that you can copy this video and build one of these like this. It's impractical, and it's not something I would recommend. What I wanted to do was show the different elements of these amplifiers and what they do and why they're there. So that's basically what I did. So I started with another one of these kits, one of these boards here, it's a different color board, but they're all the same. They're the same board, same kit, same parts, same everything. And I removed the output transistors and I relocated them to a proper heatsink. Now, a little bit about this. What I used on these were 2N3055 NPN transistors. These are very, very common transistors, very popular. They use them in all kinds of things, from amplifiers to power supplies. It's a very old transistor that was developed by Motorola clear back in probably the late 60s to, maybe 1970, something like that. There's a whole history on this very transistor that you can look up. I think even Wikipedia has a history on these. The one thing I will bring to your attention is, if you look how shiny the side of the case is and look how dull the top of the case is, this is a warning sign that these may not be authentic 2N3055s. They may be, but they also may not be. Because when you have this kind of roughed finish, this dull finish, it means they probably sandblasted the top of the cases off to remove the original markings, because it was a different transistor, and then they print on something that's more desirable. So is this a true 2N3055 inside here? I could not tell you. I don't know. What I do know is when I tested them, they tested out in a very similar manner to an authentic 2N3055. So I'll leave it up to you to discuss online what you think. But whether they're fake or real, they work fantastic in this circuit, and I don't have any reason to change them. And yes, they're cheap. Another thing that I did was I went on to eBay, I found the cheapest 2N2222 transistors I could get. I bought 500 of them for like $4 US. Yes, you heard it right, including shipping, I think. We're going to test them in some video in the future to just see about fake, real. I just want to see. Inquiring minds want to know. But that's for the future. Let's get back to this. So if you look, in order to make things a little neater layout, I made these little piggyback boards here, these two brown ones. I just cut them out with a Dremel tool, or actually with my bandsaw, and sanded them. And then, so this is the DC offset circuit. So this little board that we cobbled together here, that's what this does now, just to get it up out of the way. The bias circuit, instead of this being on top of the diode, this pot, the diode is underneath the board, and I went with a 1N4148, and you'll see this in the schematic when we go over the diagrams. We'll do that later in the video. And then you have your pot right here. And then I actually had to, because of the design changes I made, I needed 4 diode drops instead of 3. So there's 4 of the UF1004s, and no, they are not thermally coupled to this, because it really was going to get kind of messy to kind of run wires all the way over to the heat sink and try to attach them here or something. I left it here, and they seem to be working just fine. Kind of their self-heating from current seems to allow them to track pretty well. These transistors stay almost ice cold, even when you're running this amp really hard. So no problems there. Some of the design changes in the circuitry, like some of these things you're seeing in here, I'll explain that from the schematic when we go over it. I mean, even like with the, in the feedback circuit and things, there were a couple little changes I made. I removed the tail resistor, the 33K tail resistor in the long tail pair, differential pair, and I replaced it with a couple of these constant current power supplies, 2-terminal. Not necessary, total overkill, but again, we're showing proof of concept of where these things are placed in a circuit and how they work. So that's the whole reason it's in there. Is it impractical for this little amplifier? You betcha. But every little thing helps, and we'll see that here when we test this amp out. I also added a volume pot to adjust the level, and we'll get more into the performance changes, because this does perform much different than the original design. Now looking underneath, the power supply has also been relocated. You know how I changed this? Well, actually I didn't show this in the last video, but I relocated these transistors, or these capacitors, under to here and put a little bit heftier ones to allow for that 27 volts, you know, to have a little higher voltage, to get a little more, get that 21, 22 watts out of it. And I removed the capacitors from here. Well, the whole power supply is a lot better built now. If you look in here, these are 10,000 microfarad 50 volt caps. There's a proper, you know, 6 or 7 amp bridge rectifier that's mounted to the chassis for heat. There is a soft start circuit, which probably is not 100% necessary for this small of an amp. But again, I wanted to show how these are implemented, and it's in the schematic. You'll see it. So you have your soft start circuit that brings up the capacitors slowly. Then it bypasses the soft start and puts full power to the power bank. We have a fuse this time, and a proper power switch. So right, fuse and power switch right there with an indicator light. There's your volume pot up here, and then in the middle here we added some current limiting resistors for the big outputs. I added a speaker protect board, and this not only gives you a delay speaker turn on so you don't hear the thump when the amp comes on, but it also provides midpoint protection. So if you get any kind of DC offset on the speaker terminals, it'll cut the speaker terminals off, disconnect the amp from the speakers so you don't destroy your speakers. I highly recommend in a direct coupled amplifier always to have something like this in it. You can see that there is a snubber network in there, and we'll get into that later, what that does. There are a couple of resistors and some diodes and little caps. We'll get into what those are called and what they do in a little bit. And these are the wires coming from the transistors up here, and then they go down and they connect to the wires coming from the board that goes to the transistor in here. So that's really the whole underneath how it works. And then you have the speaker terminals right here and the input terminals right here, and you can see them. There you go. And that's it. All right. Simple as pie, huh? Well, not. I got carried away. All right, so let's listen to it and let's check some of the performance of it, and then we'll go over the schematics. Okay, connecting this back up. If you remember, we had to put the transformer and everything on a variac to kind of drop it down because we could not put full power on this. So now everything's just connected directly to the mains. You can see there's the plug going straight into the mains. No silliness, no variac, anything like that. Let's move this over here and let's take a look at some of the voltages, if I can do this without everything falling over. So again, our AC mains, or AC going into the power supply now is, let's see, hold on. Not on because I have to turn the power on. Yeah. All right. Now with the power switch turned on, yeah, the electrons have a really hard time getting there when the switch is off. We have a 20, 0, and 20. So there's 20 there and 20 there. See that? So you have 20 volts AC going in. And if we look at our DC power supply, and yes, I'm precariously close to all this, so you can all give me my warning about how I can be shocked. It's very good of you to be aware of that. All right, so if we go from negative to the positive rail, you can see we have about 27 volts, 26.9 something. And our negative rail is minus 27 volts. So we have plus and minus 27 volts. Okay, looking at DC offset on our speaker terminals. Less than 1 millivolt. About 1 millivolt. So let's just call it 1 millivolt. Okay, once again, if I can do this without moving my camera all over the place, turn this stupid light off. You can see I have 50 millivolts RMS going into the amp again, just like the last time we tested it with the earlier prototype. And looking at the output, we now have about 1.38 volts RMS on both channels. Very, very well balanced. So if we take the 1.38 volts and we divide that by the 50 millivolts, you can see we have a gain now of about 27.6, which is way better than that gain of 81 or whatever the heck we were getting, you know, between 70 and 80 in the earlier version of this amp. That's much more in line with what you want. And for wattage now, before we were getting like 4 watts out or 3 watts or something like that. Now we're getting a very respectable about 1/4 of a watt, 238 milliwatts. Looking at small signal distortion, there's basically no distortion. I mean, it's passing through what the, you know, what our test equipment is putting out pretty much. It's very, very low. Okay, looking at sweep linearity, we just want to make sure this thing isn't breathing again. And you could see it is absolutely flat. Totally, completely flat. And I have the 2 channels on top of one another, so channel 1 and channel 2. See if I move them apart, you can actually see it there. But there's channel 1 and channel 2. They are perfectly lined up. So both channels match, and they're complete flat frequency response as far as the amplitude output. Okay, I now switched from 1 kilohertz to a 10 kilohertz signal. Let's turn it on. And you can see it's 10 kilohertz. And look at that for THD. Holy moly. 0.088%. That's fantastic, I think. All right, so now let's see what this thing does when we take it up to clipping. Okay, as I always say on this scope, the way it's set up is this kind of purplish line is going to be our wattage, and each graticule here represents 10 watts. So it'll be like 10, 20, 30. So I'm thinking we're going to clip somewhere over 20 watts, like 20, this would be 22, 24, 26, 28, 30. So let's see where that ends up. Let's move that out of the way. Okay, here we go. So coming up, and both channels are on top of one another, and you can see they track beautifully. And there's clipping, and it clips pretty, you can see it's just clipping at the bottom and just starting to clip at the top. So very, very symmetrical clipping. So there's just about 28, 29 watts. If we take it below clipping, right there's about 26 watts per channel. There's 26, and let's look over here. That is what I'm talking about. So I would say this is a fabulous performing amplifier right now. And again, we'll get into the schematics, how this is all possible here in a little bit. But let's first put some music through it, because who cares what all this crap looks like on the test equipment, right? It's all about our ears. And yes, you're listening to a lapel microphone recording and compressed and put onto YouTube and playing back through your sound system on your computer at home. So you're not listening to what this thing sounds like, but at least you get an idea. There's some things you might be able to pick out of it. And I can listen to it and kind of give you my opinion while I'm here. So unfortunately, while we listen to this, we're going to have to hear the furnace blower in the background, because it is colder than a witch's boob in a brass bra today. Winter is here for sure, everybody, at least in my part of the world. And I'm not a winter person. I'm sorry. It's nice to have the snow around the holidays for a little bit, and then I'm ready for it to go away and go back to summer. But anyway, Tony's opinion, that's all. So let's start up Stranger Danger, because that's kind of our de facto song it's become. Flooding out the mic, ain't I? There we go. Well, what I can tell you from my end here is two things that I noticed. Number one, the stereo separation on this thing is absolutely fabulous. I mean, I can hear every little detail of difference between the two channels. It sounds very balanced. There's no sibilance at all in the high frequency, especially those kind of artificial cymbal, hi-hat cymbal sounds in this song. It's really clear sounding, and pretty amazing how this little kit turned out with all of these modifications. But again, lots and lots of modifications. We've been messing around with this thing now for, I don't know, I've had this on a bench for about 40 minutes in these last few clips I've done demonstrating it. Even with the louder volumes and things, this is room temperature. It's hardly even getting warm. And you can see there was absolutely zero crossover distortion now. It's perfect. So let's look at the schematics. I will point out the parts of the actual circuit that are being represented by the parts of the schematic as we go over them. And that'll be the last part of this video, is just going over the theory. One other quick note is that I just realized we looked at 10 kilohertz, and we looked at a frequency sweep that went up to 28 kilohertz down from 10 hertz, how flat it was. But as far as the distortion figures and everything, at 20 kilohertz, it's almost the same as at 10 kilohertz. I just wanted to give you that note there, that side note. The only thing is the Keithley, when I go to 20 kilohertz, if have filtering on and you're going out to the fifth harmonic and all those things, and you're putting the A weighting on it and everything, the sample rate and everything, it doesn't allow the meter to properly read, so you just get a bunch of zeros. It won't give you the THD. I would have to mess around with the Keithley 2015 in order for it to show. But you could put it up on the spectrum analyzer, the 3580A, and there are absolutely no artifacts whatsoever. No harmonics, nothing. This thing is crystal clear all the way out to 20 kilohertz. Okay, so this is one of the most odd-ass looking schematics I've ever drawn, because I'm too lazy to draw everything out. So this is just a copy of the printout from the original, if you remember that, on that little thing that comes with the amp kit. And all I did was, went into Photoshop or went into Paint Shop and just modified it a little bit. And this was an actual schematic that I drew on, on KiCad, and it's showing that soft start circuit and everything. And then here's just a picture representing that board. So this kind of it's not only a block wiring diagram, but an actual physical schematic all in one. Really weird. And yeah, that's, hey, Bootyfab Labs, man, all the way. Okay, so you have your signal input up here, and you have your 10K, and I used a logarithmic potentiometer, so you can use it like a volume pot. If you were just going to make a level pot, just to trim the amplifier input, and you then drive it with a proper separate preamp, then you might want to put a linear taper pot. But either way, it'll work. Goes through your 10 microfarad input capacitor. And I would want this to be a low noise capacitor. like a, what is it, a UKL series, Nichicon or something like that. And then we go through there through a 220 ohm, and you can see a lot of this stuff is original to the original amp. We haven't changed anything for that. And goes into your input pair. Now this is a matched pair of BC 550s. You could use the original 9014s, and I'm sure they would work pretty good. They surprised me how well they did work. But if you use a VBE matched pair of BC 550s, it's probably, you'll be a little bit better. The tail resistor that used to be, and let me see if I can find the old schematic here, hold on. So looking at this, you used to have this 33K resistor in here. And again, this is just me showing how you would implement this. We put a current source, an active current source in here anyway, instead. And this one's set up for, with these resistors in this combination, it's a 2N5401 and a 2N5551. And if we go over to here, that's what it looks like. These little green modules. And there's the 2 transistors and the 3 resistors and 2 LEDs. And we go back here. And that's this circuit here. And all this does is this will make a constant current source. So this is now always going to be at about 1.2 to 2 milliamps. That's it. It's just a very low current source. So this now is literally going to be a voltage amplifier, not current at all. And so this voltage comes out of here. So this is connected to the collector. And this, of course, is your feedback. And I'm not going to redo what I went over in the previous videos. The theory of how an amp works is in parts 1 through 9. So it goes into our VAST stage. Again, we're using this circuit for the DC balance, or for the offset, whatever you want to call it. It works perfectly. And no, it will not affect, nor will it distort any of the waveforms at all, the way this thing works. All this is going to do is change the offset of the signal. You can do it at this end, or you can do it at this end. It really doesn't matter. You can put your offset signal on either side, because this is a differential pair. It's just, all it cares about is the difference between the two. So if I change this, it's going to change this, the other direction. That's all. So these 2 diodes are there to ensure that this 5K resistor will never have more than 2 diode drops across it. You're going to have a maximum of about 1.5 volts there. That's it. No more, no less. And that 1.5 volts is going to be differential. So that means with reference to ground, you're only going to have half of that. So you can go a positive 750 millivolts to a negative 750 millivolts, roughly. Okay? So, and a 1N4148's a little less than 700 millivolts, so it could be a little less than that. But you only need a few millivolts here to change the offset quite a bit. So it works. Looking at our input pair, and you know what? I just realized I did not add in the schematic. Let me draw this in, because there is one component that's missing from this. And I'm going to go to here, and it's going to, as I poke through the page, I'm going to go here. Here's your plus, here's your minus, and this is 100 microfarad. If 35 volts or 50, it doesn't really matter. And this is your bootstrap circuit, and we'll get into that in a minute here, but here's your feedback, and here's one change that we did. If you look, originally in the old one, we had 470 ohms. And all this C3 does is it decouples any DC offset here from here. So basically, this cap It's usually going to be real high. Like this one, they have it at 47. I actually raised it to 100 microfarads. So it just decouples this circuit from DC and only responds to AC. And you can see I had to increase this to 1.2K. And that's one of the main things that seriously dropped the gain of this circuit. So it actually made the amp a lot more linear. It reduced the distortion by a good bit. And it changed the gain into more reasonable range. That, our gain's around 25 to 28 now, instead of being 75 to 80, something like that. So this is a 1.2K up from a 470 ohm. This capacitor and this voltage divider here is called a bootstrap circuit. And this actually adds a little bit of positive feedback. And this will linearize the amplifier even further and reduce distortion even further. And the other thing that it'll do is, if we took this capacitor out altogether, it would still work. It would still have low distortion. It would be really good. But you would have a little bit of asymmetrical clipping, for one thing. So like it would clip at the bottom a little bit before it clips at the top. This levels that out. And the value of this capacitor isn't super critical. Okay, this is kind of like, again, this is for decoupling of DC, but the signal passes through it, when it's AC. This divider ratio is really what sets that bootstrap circuit. And I have this one set kind of to a 2-to-1 ratio, so you have about twice the amount of resistance at the top than I do at the bottom. I've also seen them at 50-50, half and half. So you have to experiment. You can calculate a lot of this, but you've got to be better at math and all that stuff than I am. So I use the brute force and ignorance method. And essentially, the first thing you do is, before you worry about a bootstrap circuit at all, you want to determine the value of this resistor, the total resistance you need at the bottom of your VAS stage. Because this is setting up your bias, okay? Very important what this resistor value is. So originally it was a 4.7K, see that? With no bootstrap circuit, just a single resistor. And what was happening was, it was making this bottom half idle way, way, way too high. And even with changing the diode drops and everything, it still was not correct. So really the overall amount came in at about 6.8K to 7K was ideal. So adding this extra resistor brings that up to what? That's 6.8K right there. 2.2 plus 4.7 is 6.8. And at that split point is where you're going to come off with your capacitor, and you're going to feed some of that AC signal back up into the feedback circuit. And this is going to really linearize the amplifier quite a bit. So, and you see how it performs. Now that, I added that right up here. So if you look, and I'm just showing you one channel, it's the same on both channels. So you can see those two resistors where they connect. I just put a couple of standoffs there, and I connected the resistors in there so I can conveniently change them if we wanted to experiment. And where they combine at the middle, that's where I tacked on the cap and directly connected it to the Zobel network, because that's right at the midpoint of where the speaker would connect, and that's where that has to go here. So you can see right here, here's the Zobel network, here's that line, here's where that cap is. So that cap is going from here straight to here. Now another thing that I had to change on here, that once again is not in the schematic, is I had to add one additional diode here. And I'll fill that in just like this. So there's 4 diode drops here now, and you're going to find out why that 4th diode drop is there in a minute. So we have 4 diode drops there, and I'll get a corrected version of this, and I will actually post it up, on the screen, so you can screen capture it and print it if you like. And so, as I said earlier, this diode should never go into forward bias. This one down here, this is a protection diode. Its job is, well, first of all, let's talk about this pot here for adjusting bias. if this pot were to go open, and they do fail, potentiometers are probably one of the most high failure items on an amp board. If this pot fails open, this would become an open circuit if this diode were not in here. And as an open circuit, this side and this side would go completely up to the rails just about, which would fully turn these transistors on. They go into full saturation, and these transistors would basically fry. You would completely overheat them and they'd burn up and fail. As it is right now, if this pot were to open, this would open to 1 voltage drop of a diode, which would be about 600 millivolts. This is a 1N4148 here. This isn't about thermal tracking. This isn't about bias or anything. This is about protection. And what will happen is this will increase, this voltage here. Your bias will get really hot. The transistors will run hot. They will not burn up. That protects the circuit. And that's what this is for. You want this resistor set up in such a way that it will never allow this to get up to a forward bias. So really you want this pot, and I probably could reduce this to maybe a 200 ohm pot or something. You don't want, when this thing's wide open, you don't want any more than about 350 millivolts across here with this pot all the way, out open. And then if you turn it all the way down, it shorts this whole circuit out, and then you just have the 4 diode drops, which should turn the amp off, like put it into, where you'd have crossover distortion. And this circuit actually for these components works perfectly for that. Now, looking at those diodes and this whole mess here, this 1N4148 is now located under the board. So it's underneath here, like right under here in this area, underneath. And the pot is mounted on the top, and I just drilled a 3rd hole so that it'll just go in there, and then the 2 pins of the one end of the pot are tied together. And then here's your 4 bias diodes. These are UF1004s, and they will thermally track a little bit from forward current heat, as they're kind of like self-heating. But it would be better if we could thermally couple these to the drivers and all that. But this is just not a circuit that's very conducive to this. Again, this is a very prototype demonstration proof of concept amp. If you were going to build this commercially, you would not build it this way. It would not be fabricated like this, okay? But that's the bias circuit right there. All this little section here is your bias. Right here is your bootstrap circuit. Here are the 2 drivers. Here is the VAS, or the voltage amplification stage, and then the 2 differential pairs are underneath the constant current source. This CCS was kind of big, so I kind of mounted it on top over like that. Okay, moving along to the driver section. So that's our VAS stage. And again, a few changes from the original if you look at it. Now, if we go to our drivers, so here's your drivers, here's your outputs. I used a 2N5551 and a 2N5401, and up here I used a 2N5401. This is kind of a critical transistor up here, this VAS stage, the voltage amplifier. It needs to be a high enough gain, that it can drive this whole thing and drive the whole output section, but you don't want it to be too high of a gain. And essentially, we want to remove as much of we don't want this thing to be a low impedance load that it's driving into, because if you do that, it's going to change how this works. That's another thing the bootstrap circuit helps to do, is to keep this from being such a, go into a low impedance mode, let's call it. If we go here to our drivers, you can see I moved the emitter resistors for the drivers. You see here's our 2 emitter resistors. I moved them onto right where they were originally, onto the emitter and the collector of the outputs. And then you can see they kind of share this little current limiting resistor, which is only 30.33 ohms. It's just a third of an ohm. And there are a couple good reasons for doing this. Number one, you have direct coupling here to the emitter. But more importantly, if one of these transistors fails or you have an overcurrent situation and this resistor opens, it's not only going to disconnect this transistor, from a path to ground through the speaker, it's also going to disconnect this. Even though you have this 220 ohm resistor, if this thing goes full bore, you're going to overload this transistor and it's going to fail. So this kind of turns off this whole section up here if this resistor were to open. Same thing down here. Now's when things get a little bit interesting. All right, so when we come down, so this is all for the positive half cycle. For the negative going portion of the amplifier, I added an extra little circuit here. If you remember, this was originally just a 22 ohm resistor going to the midpoint. And if you go here now, you can see it's no longer 22 ohms, it's 100 ohms. There's this funny looking diode facing the same direction as the PNP transistor's emitter is. And you have this little 100 picofarad capacitor shunting across that. And now it's tied into this side of the current limiting resistor, such as this is. So what is this? Well, there's actually a formal name for this diode. It's called a Baxandall diode. And really, this is something you're only pretty much going to see in a quasi-complementary amp, where you have these, two like polarity output transistors. Because the big issue you have with this design is if you look at the Darlington configuration up here, you have the emitter of an NPN transistor going into the base of an NPN transistor, and then you have the emitter of the output transistor going to the midpoint. So this is seeing 2 voltage drops from your driver. However, on this one, you don't have that because you need the phase inversion of this PNP driver transistor here. That's how you get your negative drive pulse. But the problem is the output of this, you're driving the base of this output transistor with the collector of this PNP. So you only have 1 voltage drop on each side. And that causes an imbalance between these two sides. That imbalance is the cause of a lot of problems with distortion, with little ringing artifacts, things like that. And so by adding this Baxandall diode, what that does is that gives you that 2 voltage drop. This driver sees 2 voltage drops to its source, just like this one does. And that kind of evens things out a little bit. Now you can put this resistor, by the way, this is not emitter degeneration. That is not what these resistors are for on the output. These are current limiting resistors, and in most cases, like in this circuit, you could essentially jumper those out and have it the way that it was, like this, because you only have 1 pair of outputs. Where this becomes a bigger issue is if you have ganged outputs. So let's say this was a 100-watt amplifier or a 50-watt, and you had 2 outputs on each side. So you had 2 here and 2 here. Well, chances of them being exactly matched, and when I say exact, I mean to the T, totally matched. The one with the lower VBE is going to turn on harder than the other, and you will have an imbalance of current between the transistors. And what these resistors are there for is to, number one, balance that imbalance of current, so kind of take up the slack as per se, and when you have if you have a situation where the transistor overloads or shorts, this will be in there to take some of that extra current. And if it's way too much current, the transistor will actually, or the resistor will actually open. So these are current limiting resistors. And that's why a lot of people get hung up on, You need to put this one on the emitter. It's an emitter resistor. Well, they call it an emitter resistor because in most cases, in a complementary amplifier, this would be a PNP, and of course it would be on the emitters, and that's where that comes from. But it doesn't matter. You can connect this resistor on this side or on this side, and it will still limit the current. The only reason I have it here on this side, and you'll see amplifiers designed both ways, with the resistor up here or with the resistor down here, depending on the manufacturer. But again, I have this up here as protection, so that if something shorts, it's going to disconnect this end as well as this together. You know, if this amp or if this resistor opens up. So it's a very balanced circuit, and you can see that's why we have such a really good performing amplifier. You have to go through all this just to get this thing to work reliably. If this was a true complementary amp, and this was a PNP, and the emitter was connected here, and the collector was going to the negative rail, a lot of this stuff wouldn't be such an issue. You wouldn't have as many problems with that. Even back here, I mean, yes, you could still use a bootstrap circuit and all that, but this having it this way causes a lot of problems. And the funny thing is, if you ever read Bob Cordell's book, you know, on designing transistor amplifiers, if you try to look up quasi-complementary amplifier, he has about 2 sentences in that great big thick book that's this thick that basically says, this is a piece of crap and it's obsolete and we're not talking about it in this book. I'm paraphrasing it, but that's pretty much what he says. I laughed when I read that, because what if you want to know about this? What if you have one that you want to work on and you want to understand how it functions, you know? But yeah, these get a really bad reputation. But as you can see, when executed properly, it's all about circuit design. I keep saying this to you guys. You know, everybody they hear something on the internet and they repeat it. But the truth is, you can have platinum plated top of the line transistors that cost $1 million a piece, and if it's a poor circuit design, it's going to sound lousy and it's going to be a piece of crap. Circuit design, circuit design, circuit design. You have to have good layout physically of the amp, how it's laid out, you know, your lead dressing and all that, and the values and the design of the circuit has to be right. If you do it right, it's going to work great. Okay, enough of a Tony rant. So moving along here, so you could see how this thing performed. I mean, we just saw that. The Zabel network is the same as it always was. We really didn't change it. The only difference is I increased the wattage of this resistor. If the amp ever breaks into oscillation, this thing is going to get red hot and it's going to burn up. So I just put a little bit bigger resistor in there. It's like a 1 watt instead of a 1/4 watt or whatever was in there. Then I added this circuit right here. This is extremely important. It needed to be on there, and if it's not on there, you could have so what'll happen is, let me see if I have a little piece of paper here. So let's say we have our sine wave. As you increase and decrease the amplitude of this sine wave, you can get these little fuzzy high frequency ringing artifacts like this that'll show up, you know, somewhere around here on the waveform, and they look kind of like that. They just look like fuzz, like it's growing a beard right there. And what that is that's a high frequency oscillation that's taking place, and it's only taking place during part of this. If you notice, it's the same spot on the sine wave each way. And that's a little clue as to what's doing it. It's amplitude dependent, okay? And what's happening is this whole amp, you know, it is a reactive circuit. It has reactive components to it because these transistors have Miller capacitance. In other words, they have a little bit of capacitance in them. And what happens is, as that capacitance builds up and goes down and so forth, once you cross through a certain amplitude there, the phase angle, leading and lagging of current and voltage in in the different parts of the amp will become such that you will actually have positive feedback within the transistor. And when a positive feedback, when that occurs, you get oscillation. That's what an oscillator is. It's a positive feedback amplifier. But it only does it during certain amplitudes, because after the amplitude of that signal crosses through that, it's either too high or too low. It changes that phase angle enough that it won't oscillate anymore. So the oscillation extinguishes itself. But you'll see these little artifacts in there. This prevents that from happening, because that only happens when you have a reactive component on your speaker load. So like the speaker is also a reactive component. It's not a totally DC resistive component. So what's going to happen is that they are going to not get along with one another, and that's what's going to cause that oscillation. When you put this kind of snubber circuit in here, this is just a few turns of really thick wire. It's microhenries. Anywhere from 1 to 2.5 microhenries is what these are going to be. So you can take a drill bit or something and take some thick wire, like this kind of stuff. This is number 16. You could 16 or 18 gauge, and you'd put maybe 10 or somewhere between 10 and 15 turns around a drill bit, maybe a little smaller than this pen diameter, and you shunt it with a 10 ohm resistor. And that's going to be just enough reaction there to break up that oscillation from happening. So if this isn't there, there's chances under certain situations where you would get this. This prevents that from happening. And that's why it's in there. So if you look underneath the amplifier, let me get you on there, you can see where I fitted those in there. So looking in here, here's the coils, and you can see I didn't do a super neat job on it. It doesn't need to be. It works just as it is. And this resistor, here's your 10 ohm resistor. There's the other 10 ohm behind it. And this is, left channel, right channel. These are those 4.33 resistors that goes to the emitter of one side and the collector of the other side, of the push-pull pair. This is the Baxandall diode up here, if you see it, behind this capacitor. And again, this capacitor is shunted across that diode, because when that diode switches on and off, all right, what's going to happen is you're going to get switching noise, which can cause a little oscillation. This tiny little 100 picofarad capacitor prevents that switching noise from happening. Everything's there for a purpose. There's your 220 ohm resistors. There's one here and there's one over here for the two channels. And again, like I said, this is the whole section where the transistors combine to the actual circuit board. And then you have your output wires from that network right here, from the little snubber network, comes out and goes to the input of your speaker protect board. So you have left, right, and your ground in the center, and then you have your output. And these are controlled by these two relays for left and right channel. So when these relays drop out, it will disconnect this connector from this connector. When the relays pull in, it connects the wires from this connector to the wires on this connector. And then that's all controlled by this little UPC, I forget the name of the chip, 12 something speaker protect IC. Very slick. I like the way it works. Now another thing we can do is you can measure your bias voltage or your bias current by reading the voltage drop across this resistor and then doing the math. And I just set this for about a voltage drop across here of about between 10 and 15 millivolts is all you need. And you're going to want to measure the lower ones down here. So you're going to want to measure this one down here, because it's the one that's going to idle a little higher than this one here, because again, it's a quasi-complementary design. And I'll demonstrate that, because this does not work like a true complementary. So if I go from the midpoint, which is this is where your speaker would go, I'll put that on the negative probe, and I go to resistor or the Q13s, See how I have about 10 millivolts right there? But if I look at the upper half, which is Q11, it's only about 1.2 millivolts. So you would think that there's an imbalance, and there is. At idle, that's how these complementary amps work. And we're talking current, not just voltage, you know what I mean? We're talking about current. So if I look at Q, well, I showed 14 and 12, but it's also the same as 13 and 11. See there, 13, 11, 14, and 12, just the two channels, right and left. And this one down here, when we measured here, we had a little bit higher idle current than we do up here. And that's what you're going to see. The negative half cycle with this particular design, the way this works, this side is going to idle at a little bit higher current than this. It's still very, very, very low. And it all equals itself out when you put a drive signal into it. But that's what you're going to see. That's how these work. Again, we're talking about a quasi-complementary. It's a full complementary amp that has a PNP down here and an NPN up here. Totally different how it works. So that's how this amp works. And those are all the different components. And you saw how well it performs. And going up to the power supply, that's the only last part we need to cover. I'll zoom in on it. So AC mains comes in, it goes through the fuse, through the switch, and here's that relay, and that's on that board. Okay, so looking up here, here's the board, here's the relay, here's the inrush current limiter, and here's the monitoring dropping resistor. So if I go down here, again, here's that inrush current limiter, that black disc. This is a negative temperature coefficient. So what happens is this starts out at maybe about 10 ohms or so. And then when that inrush current goes through there, as this starts to heat up, it will drop in resistance till it'll almost go down to below 1 ohm. And then it'll stay hot. That's the thing why you don't want to leave it in circuit. You could just leave it in there and not have this, but this will get really hot, and I don't like having a hot ICL sitting in heating the inside of my amplifier. So what's happening is this is connected to negative VCC. So it's connected right here. And this is connected through those two resistors, which comes up to about 2.7K, into the plus VCC. So what happens is this thing turns on, it's limiting the current. These caps are starting to charge, and they want to have infinite current. They want to charge up right away. So they're going to put almost like a short circuit in the beginning. So all that current is going to be limited by this. Once this voltage builds up, that current will drop. As the voltage builds up, the voltage across this coil, between here and here, because that's what this is. This coil of this relay will build up until finally it gets into its pull-in voltage. It's a 22 volt relay. When it gets to about 16, 17 volts, this will pull in. And once this pulls in, it's going to jumper this out of the circuit, so this will cool back down right away. So it's ready for the next time you turn it on. And then basically this is just like a straight piece of wire through here, allowing full power to the power supply. And we have these little bypass 470 nanofarad caps, and those will help even reduce the ESR at high frequencies to these even better. So all good stuff. And this also acts like a bleeder circuit because it's shunted across here. So when you turn the power off, this relay coil will bleed down these caps. And when they get down low enough, this will drop out. If it doesn't fully bleed them down and you flip the switch back on right away, the caps are already partially charged, so they're not going to draw heavy current. So this doesn't need to be in the circuit. So this will be in already because it's not dropped out yet, and it'll just come back on. Very elegant, simple circuit. So that's how that works. So very simple power supply. There's no regulation or anything like that. And this amp is absolutely dead silent. I can turn it on. Actually, it's on right now as we speak. let me take the microphone. I have it off here. I will put it right in front of the speaker, and you can tell me if you can hear any hum or not. I can't hear a thing. So that is it. I mean, I have a little bit of buzzing here on my bench from some of the power supplies to the bench, but other than that, dead silent. There's no noise on this amp whatsoever. So there's the complete circuit. And between this and the last 9 videos, I hope that you at least have some basic idea of how an amplifier works. So that wraps up part 10. And I'm really excited to get back to some of my current projects that have been waiting for me to finish this. And I did get those panels back from the powder coatings company, and they look great. So that Pioneer Spec 4 is going to be an awesome looking amplifier when I get it done. I can't wait to finish it. So with that, I am going to wish you all peace, joy, happiness, and good health in your lives. And well, I got a little carried away. I didn't expect it to end this way. I didn't think I was going to actually build an amplifier and drill a bunch of holes here and, But I figured I wanted to bring it all together to combine all of our ideas and actually make a functioning, properly designed amplifier. All right, I hope you enjoyed it. I, again, wish you all the best, and we'll see you again real soon. And we'll be back with more projects to come. Take care, everybody. Bye-bye.